We are continuing on here. We're talking about types of reactions last time. And as we talked about last time, really reactions and equations can be really classified in multiple ways, sort of depending on what you're looking at. Again, you can take one reaction and you can classify it in many different ways, depending on sort of the aspects that you are looking at. But pretty much there's three reasons why pretty much most reactions take place. And really the three reasons, again, that most reactions take place is the formation of a solid or a precipitate, the formation of water. It's another main reason why a reaction takes place, and really the transfer of electrons. So pretty much most reactions that you come across will boil down to really one of these three things is really the central sort of thing that is happening in that reaction. When we talk about sort of classifications of reactions, you could think of it as there's really kind of two big classification of reactions. There are the ones we focused on last time, mainly, which are double displacement reactions. And double displacement reactions, as we saw a number of times, you could always recognize these guys by pretty much what you are reacting with. And it is two ionic compounds in which they will basically switch partners. And as we saw, we'll form some new ionic compounds on the product side. And the result of this sort of double switch or exchange that sort of occurs is one of two things will happen. Either, again, one of these guys will make a solid and a precipitate will form. And that is a more specific sort of classification of a reaction as a precipitation reaction. The other thing that might happen is one of these guys may form water. And that is usually a result of a more specific classification of acid-base reactions or acid-base neutralization reactions. So kind of double displacement reactions really take care of almost like two of the three reasons why a reaction takes place. Either you're going to end up making a solid, you're going to end up making water. And again, those are the main sort of draws as to why that reaction took place. So what we're going to focus in on here on the last part here of this sort of lecture is the third sort of reason why a reaction takes place, and that is a transfer of electrons. Those type of reactions fall under the big category of redox reactions. And redox reactions is pretty much that, the transfer of electrons. And again, the third sort of reason why a reaction will take place. As we will see here today, under this sort of big category, will be several more specific ways to classify a reaction other than a redox reaction. But these are pretty much going to be your guys like your synthesis reactions, your decomposition reactions, your single replacement reactions. These more specific classifications sort of fall under this umbrella here of redox. So we kind of have with reactions two big umbrellas, really sort of general what's happening and more specific ways of classifying these guys as we go through it. We talked about with our double displacement last time also things like solubility and solubility rules. We also talked about different types of reactions like our molecular equation, our total ionic equation, our net ionic equation. And again, those are the type of reactions or equations that really sort of display what is happening in that particular equation and what is going on. To an extent, you could also do some net ionic equations over here as well, and we'll talk about that a little bit as we go through with like single replacement reactions as well. Any questions on any of that stuff there? All right, then let us get into really the kind of big second part of it, which is redox reactions. And let's just in general talk a little bit about redox reactions. We're going to talk about later on in lab as well. But redox reactions are basically two types of reactions. They are oxidation and reduction reactions. And typically, what happens is these two things basically happen together, which means if you have somebody that is going through oxidation, you should have somebody that's going through reduction and vice versa. So one of the good things about sort of redox reactions is if you're able to maybe determine, for example, okay, this guy's going through oxidation, by default, really the other substance has to go through reduction, or vice versa. If you're like, I know for sure this guy is being reduced, I then know that the other guy is being oxidized. So that's one of the nice things about it is they always sort of happen together. And really, if you're able to identify one thing, one part of that, the other guy is happening and the other thing's happening to the other substance that's present. So let's talk a little bit about some of these definitions of oxidation. And for the most part, in chemistry like this and most general chemistry classes that you take, when we talk about oxidation and reduction, well, a lot of times we do talk about it in terms of electrons. So oxidation means that somebody has lost electrons, and reduction means that somebody has gained electrons. Some people like to remember it like Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig and he goes grr. You don't have to choose. You can use all of them together. It all works. But that's a quick way to sort of understand what is happening when we lose electrons or gain electrons. I would say probably 9 times out of 10, and probably most of your cases, these are the two definitions of oxidation and reduction that you will see the most. There are some other definitions of oxidation and reduction. For example, oxidation also means that you have gained oxygen as you go from reactants to products, or you have lost hydrogen as you've gone from reactants to products. For reduction, it also can mean that you've lost oxygen as you go from reactants to products. And for reduction, it could also mean that you've gained hydrogen as you go from reactants to products. I would say that these two definitions, sort of the losing and gaining of oxygen or hydrogen, are most often found a lot of times in organic chemistry. So if you take organic at some point, you will see these definitions again. And the reason for that is most organic compounds are nonmetals. So when we have sort of nonmetals and nonmetals together, a lot of times it's easier to follow. Did that guy kind of gain oxygen, lose oxygen, or gain hydrogen or lose hydrogen? It's much easier sort of in inorganic chemistry where we have metals and stuff like that. We can figure out oxidation states, charges, and sort of what's happening and be able to figure out what is being oxidized and what is being reduced. Questions on that there? So again, for us in most of their general chemistry classes, these again are pretty much the definitions that we look at when we think about oxidation and reduction. Now, when we talk about oxidation and reduction, is there a question? Yeah. It is hydrogen. It is in the sense of usually organic chemistry and stuff like that. It's H2. It's actually two hydrogens that actually are either gained or lost. And in that case, yeah. In terms of oxygen, a lot of times it's just actually just the O being put in. And there's a lot more to it than obviously just the O gets popped in there. But usually what ends up happening is it has more oxygen than started with. Or in terms of hydrogen, it usually will gain kind of two hydrogens. It's usually, and it's in the form of H2. Yeah. Other questions? Now, when we talk about what is being oxidized and what is being reduced, that is different than a couple other terms that sometimes confuse people, which is the oxidizing agent or the reducing agent. And the oxidizing agent is the substance that gets reduced. And the reducing agent is the substance that gets oxidized. So you may be wondering, why does it sort of have the opposite name? The reason it has the opposite name when we're talking about the agent, either the oxidizing agent or the reducing agent, is because, for example, the oxidizing agent is something that gets reduced. In order for it to get reduced, it has to gain electrons, which means it has to cause somebody to lose electrons. Hence, it is causing the oxidation of something else, and that is why it's known as the oxidizing agent. Same thing with the reducing agent. It is the thing that gets oxidized, which means when it loses electrons, somebody has to gain the electrons and gets reduced. So it's causing the reduction in the other thing. So when you talk about, or if you're asked the question of what is the oxidizing agent or the reducing agent, that is a different question than what is being oxidized and what is being reduced. So that's a really important distinction. When you're talking about the agents, it's just really the opposite thing of the name of what's happening. When we talk about also oxidizing agents or reducing agents, those things, by the way, are found on the reactant side. Yeah. So those are the things that are found on the reactant side of the arrow is where you find both of those things. Any questions on that? Yeah. Yes. Yes. And that's basically what is happening, because that's basically the basis of this reaction is the transfer of electrons. So somebody's going to lose some electrons, somebody's going to gain some electrons. All that's happening on the reactant side. And obviously the result of that would be on the product side of the arrow. So when we look at oxidation and reduction, we also will sometimes try to figure out sort of what is happening. So there's usually a very simple way that you could figure out, is this substance being oxidized? Is this substance being reduced? And if we just think about the definitions there of oxidation, really the electron definition, again, losing electrons, and obviously reduction here, gaining electrons. We should know at this point pretty much what happens when these two processes occur. And you can use an actual just basic kind of number line where positive numbers are to the right of 0 and negative numbers are to the left. And you can figure out what is happening as you look at a substance on the left-hand side of the arrow, or an element on the left-hand side of the arrow, which is the reactant side, to what happens to it on the product side. So really what you want to look at is what's known as oxidation number. And that's kind of like the charge, but not exactly the same. But it's kind of like the charge that something has on the reactant side of the arrow versus what it has on the product side of the arrow. And if somebody loses electrons, you would expect it to now become more positive, right? Because it has more protons than electrons, so it becomes more positive. So if you look at some type of element or substance really on the left-hand side of the arrow, and you find the same element on the right-hand side of the arrow, and you see that its oxidation number, or sort of its like charged sort of situation, is becoming more positive, or even just moving in this direction on the number line, which is more positive, that means that that thing is going through oxidation. Vice versa there, if something is going through reduction, it means that it has gained electrons, which means it now has more electrons than protons. So it should become more negative in that case. And if you look again at the oxidation number as you go from reactants to products, it's going to become more negative. So if you're on the number line and kind of moving in the more negative direction, is going to be going through reduction. So that's a very sort of straightforward way that you can sort of use the oxidation number. We're going to talk about how to figure out oxidation numbers in a second, of what's going on the reactant side versus the product side, to basically figure out. So for example, if we look at something like, say, sodium, right? Metal, no charge, and sodium becomes an ion like this. And an electron, right? So if we look at sodium on the left-hand side here, for example, it is by itself. And just so we're clear, any element, anything that you have from the periodic table, any of those diatomic molecules, that are elements. They pretty much are uncombined and they have no charge and no oxidation state. So sodium metal by itself basically has an oxidation state of 0. It has no charge or anything like that. Sodium with a +1 charge obviously has a +1 charge happening here. So if we look at it in terms of the number line, my sodium on the left started at 0 and it ended at +1, which means it is moving in this direction and is becoming more positive, which means here in this case, our sodium is going through oxidation. By the way that we represent an oxidation reaction is electrons are on the product side. And that is like it is being given off, right? Being released and being given off. So we always see electrons on the product side. Now, if we took something, say, like chlorine here, and we do this type of deal. Now, in this particular case, if we look at chlorine here on the left-hand side, the Cl2, in terms of the Cl2, again, that is naturally how chlorine comes, uncombined, has an oxidation state of 0, basically kind of no charge. Cl minus is chloride, has a -1 charge. So if I go to my number line, I'm starting at 0, and I am ending at -1, which means it is moving in the more negative direction, and this guy is going through reduction here. And we can see that it's going through reduction because we actually will see the electrons on the reactant side. These two things, by the way, are what are referred to as half reactions. That is the reduction half reaction, and the top one is the oxidation half reaction. They are half reactions because they are pretty much half of what is going on, which means I could get the overall reaction by adding these together. Before I add these together, though, there's one thing when you look at half reactions that you always need to make sure of, which is when you take an oxidation half reaction, which is half of the reaction that's taking place, and you take a reduction half reaction, which is half of the reaction that's taking place, when you add them together, you need to make sure that you have the same number of electrons in each half reaction. And that is because the idea here is the guy being oxidized is going to lose a certain amount of electrons, which means the person being reduced needs to gain the same amount of electrons. So when you look at the half reactions, you need to make sure they always have, before you go, for example, to add them back together, to get the overall reaction of what's happening, you do need to make sure that they have the same number of electrons. In this particular example that I wrote up here, they do not have the same number of electrons, right? The first half reaction has 1 electron. The second half reaction has 2 electrons. So what you would typically need to do is, before you add them together, is take the first one, for example, and multiply everybody by 2. And that would give you 2 sodiums, goes to 2 sodium ions and 2 electrons. The bottom half reaction, we didn't do anything to, so we still have 2 electrons, and our chlorine goes to 2 chlorides. Now we have the same number of electrons in each half reaction. We have 2 and 2. Now we can actually add these back together. The idea is when you add a half reaction back together, an oxidation half reaction and reduction half reaction back together, the electrons should always completely cancel out. So you could think of like the arrows here as like equal signs, and anything that's on opposite sides of the arrow that is exactly the same or the same thing could either completely cancel out or reduce down. So in this case, I have 2 electrons on the left-hand side of the arrow and 2 electrons on the right-hand side of the arrow. So they essentially cancel out, almost like you just subtract it to the other side, and they kind of cancel each other out. At this point, there's really nothing else that's going to cancel. And what happens at this point is everybody on the left-hand side of the arrow stays on the left-hand side of the arrow. Everybody on the right-hand side of the arrow stays on the right-hand side of the arrow. So if we just bring down on the left-hand side, we have 2 sodiums plus chlorine. goes to 2 sodium ions plus 2 chloride ions, which, by the way, make 2 sodium chloride, right? Like an ionic compound here. It'll make 2 of those guys when they come together. This is the overall reaction that is happening here. It is basically a transfer of electrons from the sodium to the chlorine, basically. So the sodium is losing electrons, the chlorine is gaining electrons, and this is your basic redox reaction that's basically taking place. Any questions on that there? By the way, here in this particular example, my oxidizing agent would be which thing? Which one would be my oxidizing agent? My oxidizing agent is the thing that gets reduced, yeah? So in this case, it is the chlorine, right, that is being reduced. That would be my oxidizing agent. And the sodium over here, again, on the reactant side, would be my reducing agent in this case, as it is causing the reduction of chlorine, and the chlorine is causing the oxidation of sodium because it needs those electrons basically to get reduced. Any questions on that there? So you could also use this, for example, if you have, perhaps even, things with charges on both sides. So let's just say I had Fe3 plus on one side of the arrow and Fe2 plus on the other side. Is this being oxidized or reduced as iron? Ideas, 50-50 shot. What do you think? So if we is being oxidized, so let's see. So if we look on the left-hand side of the arrow, my iron is starting at +3, which would be in this ballpark-ish. And on the right-hand side, it's at +2, which means it needs to actually move to the left, which means it's becoming more negative, and it's actually being reduced in this case, yeah? So it's actually going through reduction. So that's, again, how you can use that number line very easily to figure out, what is happening. It's moving towards the more negative side, so it's going through reduction. Any questions on that? If you think about it again, when it goes through reduction, it's gaining negative electrons, which means its positive charge has to come down, right? So that's what's happening there. And when somebody loses electrons, its positive charge goes up because it lost electrons, again, has more protons and becomes more positive. Any questions on any of that there? So as we just looked out there in that example, we're really looking at an oxidation reduction sort of reaction that's happening. For example, here, if we take magnesium ribbon and burn it in a Bunsen burner, maybe you've done that at some point or not. I don't know. They do that anymore in some of these classes. But you burn the magnesium ribbon and they tell you, observe what happens, but don't look directly at it because you'll be blinded because it's a very, very bright light that happens. But overall, we're going to take magnesium and going to make it into magnesium oxide. So when we look at the magnesium, again, magnesium here by itself, uncombined, has no oxidation numbers, 0. Has a 0 oxidation number, I guess the way to put that. Magnesium with a +2 charge has a +2 oxidation state. Once again, we could go to our number line if we're not sure. And we're starting at 0 for magnesium and ending at +2, which means it is moving in the more positive direction. So as you can see here, it is going through oxidation in this particular case. That again is why we see our electrons there on the product side. For our oxygen, which is naturally how it comes, that is 0. And making oxide ion, which is -2. So once again, starting at 0, ending at -2 is moving in a negative direction. So that is why that is the reduction half reaction. Once again, as I mentioned before, we see electrons there on the reactant side. It tells you it's a reduction half reaction. Once again, we could add these together and keep everything on the left-hand side on the left and the right-hand side on the right. And as you can see, at this point, our electrons will cancel each other out. and we will end up with the overall reaction, which is, once again, in this particular case, our magnesium is again transferring electrons to the oxygen. And this is exactly what we should expect to happen in a ionic compound, as we should know. In an ionic compound, when we have a metal and a non-metal, which one loses electrons typically? It is the metal that loses electrons, right? That's why they become positively charged in cations. And non-metals are typically the ones that gain electrons and become negatively charged, or anions. So it's really simple to figure out when you have an ionic compound being formed, a metal and a non-metal coming together. The metal should always be the one that loses electrons and being oxidized. The non-metal should always be the one that gains electrons and is becoming reduced in that case. So it's pretty straightforward, again, when you're dealing with sort of metals and non-metals sort of coming together in this type of reaction, to figure out what is being oxidized, what is being reduced. But again, some situations you may have multiple metals on the left-hand side and right-hand side, so it's good to understand how to do it with the number line there. It's a pretty straightforward way of doing that. In this particular case, the magnesium here, with no charge, by the way, is our reducing agent as it is being oxidized. The oxygen here, which is being reduced, is our oxidizing agent. Yeah, so again, those things are found on the left-hand side, not just the right-hand side. Any questions on that there? All right, so redox reactions are really important classification reactions. As I mentioned before, they are really the big umbrella of sort of a type of reaction that's happening. The ultimate thing that's happening here is our transfer of electrons, and that again will give us a more specific way of classifying reactions as you go through it. Electrochemistry, if you take 200B, you'll have a whole chapter on electrochemistry, but that is all redox reactions that happens when you do like a galvanic cell or anything like that. By the way, what happens when you take a piece of metal like you can see here and you have it in a solution? So typically speaking, if you have this sort of metal piece in a solution of ions, when you have a solution, that is where you have your ions floating around. So in the solution is where you have your ions. Here you have a solid piece of metal that has no charge on it. And what happens is, as this reaction takes place, the guys that's on the solid metal will jump off and become positive charged. They'll go for a swim. So they'll jump off of the metal into the liquid part and basically start swimming around. Those guys that will do that will lose electrons, and those guys that lose electrons will cause these guys to jump out of the solution and onto the metal, which is, as you can see here in this picture, that's what the metal looked like before they got in contact with the solution that had ions. All those ions jumping out of the solution there is basically what is plating on the metal in this particular case. So that is zinc up on top, and that is copper 2 sulfate. So in that particular case, what you have is you have zinc and you have copper 2 sulfate. The zinc is going to jump off of the solution and become +2 charge. It will lose 2 electrons that will be gained by the copper and reduce it to solid copper that will start plating the metal basically and come out of solution. So again, that change of transfer of electrons causes also, as you can see, sort of a change that happens. Ions are always in the solution floating around. Things that have no charge or oxidation state are more of a solid type situation. In most cases are a gas type of thing. And that's sort of what we see here again as well. They're jumping out of solutions and coming into solution. What will happen if you let this go for a while is eventually all the blue in the solution will kind of change from blue, because the blue is caused by the copper 2 ions. So as they keep jumping out of solution, there's going to be less of those copper 2 ions, and the blue color will actually start to dissipate a little bit as it sort of jumps onto the metal. So if we look at this, one type of sort of redox reaction is what is going on here. And if we look at this reaction, let's just try to figure out what is going on here. So we have zinc on the left-hand side, and once again, the zinc on the left-hand side is not attached to anything. It's uncombined. It has an oxidation state of 0. This is copper 2 sulfate, which means the copper here has a +2 charge. The sulfate overall has a -2 charge. On the right-hand side, the zinc is now hooked up with the sulfate. And at that point, the zinc on the right-hand side has a +2 oxidation state. Sulfate is still -2. And the copper is by itself. So this is, as we've talked about before, a more specific type of reaction, which is known as a single replacement reaction. And what is happening here is the zinc is coming in and kicking out the copper in this particular case, right? So if we look at this in terms of what is happening here, take a moment and decide what is being oxidized, what is being reduced here. So take a moment and think of what you think it is. Okay, so let's take a look at the zinc first. So on the left-hand side, we can see that the zinc here is starting at 0. And it is ending at +2 on the other side, which means it is becoming more positive. And that means that the zinc here is going through oxidation. We also can see if we look at the copper here, the copper is starting at +2, which is like over here. And it's ending on the right-hand side at 0, which means it is moving in this direction, becoming more negative. And it is actually the copper here that is being reduced. How about the sulfate? Anything happen with the sulfate? Nothing's really happening with the sulfate, right? It stays the same on both sides, so there's no change happening. So we can, much like when we look at this, by the way, as well, that would mean that the zinc here, which is being oxidized, is my reducing agent, yeah. And the copper 2 here on the left-hand side, which is being reduced, is my oxidizing agent in this particular case. Now, this type of reaction, which is really a single replacement reaction, we could also write a total ionic equation and a net ionic equation like we did with our double displacement reactions. So if we were to do that, for example, and write a total ionic equation here, our zinc, let's say together, obviously, because it's a solid. Our copper 2 sulfate would break apart into ions. On the right-hand side, our zinc sulfate would also break apart into ions because it's ionic. And our copper, which is a solid, obviously will stay together. When we look at our total ionic equation, we can still find spectator ions, which in this case is actually just the sulfate, which, as you just mentioned, did not change over this reaction, which is why, because it's just floating around having a good time. It's just a spectator ion happening. That leaves us our net ionic equation of what's happening here, which is the zinc plus the copper 2, which is floating around in the solution, will make zinc with a +2 charge that goes for a swim, and the copper will then come out of solution as a solid. So what is happening here, once again, is our transfer of electrons from the zinc, in this case, to the copper. And again, our zinc going from 0 to +2, and our copper going from +2 to 0. That is ultimately what is happening here, the transfer of electrons that is happening. So as you can see, even in these type of reactions here, these redox reactions, you can write, for example, in this sort of single replacement situation, basically a net ionic equation as well to describe what's going on. Questions on any of those there? All right, so why don't you try the bottom there? Copper wire reacts with silver nitrate to form silver metal. What is the oxidizing agent in this reaction? Let's see what you come up with. I'll help you with the reaction here. So we have our copper, which is solid, react with silver nitrate. This is your classic single replacement reaction. This guy is going to come in and kick out the silver. The result of that is actually you'll make copper 2 nitrate plus some silver that comes out. All right, so that is the reaction. To figure out what is the oxidation. Okay, so let's take a look. If we look on the left-hand side, we'll start with the copper. On the left-hand side, copper is 0. And on the right-hand side, that is copper 2. If you weren't sure if it was copper and copper 2, you can look on the left-hand side here for our silver. Silver on the left-hand side is actually +1. And on the right-hand side, it is 0. And obviously, our nitrate here is -1 on both sides in this particular case. So if we look at the copper, copper is starting at 0. If we go to our number line here, and on the right-hand side, ending at +2, which means it is moving in the more positive direction, which means my silver is going through oxidation, right? We look at my copper is going through oxidation. If we look at the silver on the left-hand side, the silver on the left-hand side is a +1, which is like here. On the right-hand side, the silver is ending at 0, which means it is moving in this direction, the more negative direction. And that means that the silver here is going through reduction. And once again, here our nitrate is not going through really anything on either side. Now, because of that, we know that the copper, which is going through oxidation, should be my reducing agent in this case. And that would mean that is actually the silver with a +1 charge that's going through reduction is actually my oxidizing agent. Any questions on that here? Once again, if we take this through our total ionic equation and net ionic equation here, so if we do our total ionic equation here, again, we would have copper. Our silver nitrate would break apart into ions. Our copper 2 nitrate would also break apart into ions. Remember that that 2 comes in front when you do this there. And our silver would stay together as it is a solid. In this case, we will once again see we actually only have one spectator ion, which is our nitrate. And if we get to our net ionic equation, that is the copper plus the couple of silver ions, making our copper with a +2 charge and a couple of silver solids there. And ultimately, again, what is happening here is it is sending, again, electrons over to the silver in this particular case. Any questions on any of those equations or what's going on? All right. So again, the number line, a really easy way to figure out, what is being oxidized, what is being reduced. You do want to follow really the oxidation number from the left to the right. And as you can see, you could also write sort of net ionic equations very similar to these. I think that study assignment that you have has maybe a couple of these sort of single replacement type reactions in there as well, where you have to do that net ionic equations. Any questions on that? So let's talk about exactly how you assign oxidation numbers so that you're able to, when you look at something, be able to figure out what is happening from the left-hand side of the arrow to the right-hand side of the arrow is really important, especially when you're dealing with these redox reactions, to be able to identify the oxidation number. Some people call it the oxidation state, whatever way you want to call it. The oxidation number, or state, is the charge the atom would have in a molecule when it or an ionic compound if the electrons were completely transferred. So a cautionary note is, as you will see, the oxidation number or state is different sometimes than what we think of as charges for certain elements in ionic compounds. So if the thing's in an ionic compound, it's what we normally sort of think about it in terms of its charge, will really be its oxidation number. But there are certain elements that are in covalent bonding situations where they're sharing electrons, that they will actually have an oxidation number that is very different than the charge it has in an ionic compound. So there is a difference between those two things, the charge and the oxidation numbers. And sometimes they are the same, and other cases they are actually different based on sort of the bonding that's happening with that particular element. So we'll start with the simplest ones to identify, which is pretty much any element that is uncombined by itself. Anybody you grab off the periodic table by itself that's not attached to anybody else will have an oxidation number of 0. So those include things like H2, O2, N2, those type of things. They will all have oxidation numbers of 0. If you have just a monoatomic ion by itself, just an ion, the oxidation number will be as charged. So if you have an iron 3 ion floating around, then the oxidation number is +3. If you have, oxide moving around, it is a -2. When you're assigning oxidation numbers, perhaps the best element to start with is usually oxygen. In a lot of cases, oxygen's involved, not always, but in most cases, oxygen's in there somewhere, and that's usually a pretty good place to start. Oxygen will usually carry a -2 oxidation state. The only exception is if it is actually peroxide and not oxygen, so like hydrogen peroxide or something like that, sodium peroxide, and that is a -1 because it's actually one of those polyatomic ions, peroxide, versus just oxygen. I would say probably 9 times out of 10, if you see an O in a formula, it's probably just oxygen, and maybe even more than that. But it can be peroxide, and usually, again, the extra 2's kind of hang around if it is peroxide. When you look at the formulas, that's a very common sort of thing that happens. The oxidation number of hydrogen is +1, except when it's bonded to a metal, then it's like hydride, which is -1. So if you had an LiH, the H would be -1 in terms of that. All group 1 are +1, group 2 are +2. Fluorine is always -1. When you add up all the oxidation numbers together, it does need to equal the overall charge on the molecule or ion. So if the overall charge is 0, when you add up all the oxidation numbers, it needs to equal 0. If the overall charge, for example, is like a polyatomic ion, has like a -2 charge, then you need to add up all your oxidation numbers and end up with a -2 charge overall. So it does need to equal the overall charge. The oxidation numbers do not have to be actually integers. For example, superoxide there is -0.5, so it can actually be not a whole number, the oxidation numbers. Most of the time, you'll probably come across most things are whole numbers, but it doesn't necessarily have to be. So for example, if we're looking at our friend bicarbonate here, hydrogen carbonate, and we want to assign the oxidation numbers for each of the elements within hydrogen carbonate, I would approach it this way, which is when you have a 3-pack like this of elements sort of together, usually you want to go kind of right, left, and save the one in the middle for the end. And since there's oxygen here, that's a good place to start. We know that oxygen should be -2. There are 3 oxygens, which gives the oxygen kind of an overall -6 sort of charge that's happening. If we go to the left-hand side, hydrogen is going to be +1, which is +1. That means this overall thing does have a -1 charge, so it does need to add up to a -1 overall. So if we just look at what we got going on right at this point, we have -6 and +1, which is -5. We do need to leave a -1 left over, which means in this case, the carbon is going to be +4. And that will give me +5, and -6 gives me a -1 overall. If you were to give the oxidation numbers for each of these elements, this is the proper way to do it. It should have the charge, even if it's positive. So +1 for hydrogen. Carbon would be +4. Oxygen would be -2 only, not the grand total. So that's a very common mistake that people make, is they kind of give like the grand total of all the oxygens together. When you're asked to give the oxidation number or state of an element, it's just like if you took one by itself, what that would be for it. So you would want to do -2. And again, they should have the charges as you assign the oxidation numbers. Any questions on that there? All right. So as you can see here on this table, things have a lot of different oxidation numbers. For example, as I was talking about before, when we think of, like, for example, oxygen, right? We think of oxygen as being -2, but as you can see, it can also be +1, +2 as well. Sulfur also we think of as -2, but it could also be some pluses and stuff like that. Chlorine, as you can see, we think of -1, but look at all the different positive ones it could have. And again, this is what I was mentioning before. The oxidation number and the charge we associate in ionic compounds are not always the same thing, uh, depending on the sort of the bonding situation. Okay, so let's take a look, see how you're doing. We'll start here, bottom left. Again, when oxygen's involved, definitely a good place to start. So we know our oxygen should be -2. Once again, there are three of them, which gives us sort of a -6 for the oxygen part of it. Going again, leaving the guy in the middle for the end. Going to the left, there's sodium, which is group 1, which means it will have its normal sort of +1 oxidation state. In this particular case, it does equal 0, right? So we need to add it up to 0. So the I in the middle here to get us to 0 would be a +5 situation. So our sodium would be +1, our I would be +5, and our oxygen there again would be -2 in terms of its oxidation state. Any questions on that one there? Coming up here on top, IF7, so fluorine's always -1. That gives us like a -7. That means iodine here is going to be +7 to balance it out in this particular case. And that would mean that I is carrying a +7 oxidation state. The F here is carrying a -1 oxidation state. Again, not a -7. Any questions on that one there? So again, different as you can see here for these couple of things. I we normally associate as -1 in an ionic compound. F as well. I'm sorry, I we associate as -1 and +7 on the top there. Coming down here to potassium dichromate, we got a -2 there for our oxygens. It's like a -14 since there's 7 of them. Our potassium, which is group 1, should be +1. There's 2 of them, which gives us a +2, and that's going to give us an overall charge here of 0. There happens, though, in this case, to be 2 chromiums, which means if we just take 14 minus 2 is -12, divided by 2 is 6. That means that each of the chromiums here has to carry a +6 charge, or oxidation state, really, which will give us a +12, which will equal 0 in this case. Here, potassium being +1, chromium being +6, and oxygen here being -2. Any questions on that there? So why is something, for example, like iodine or like chlorine, positive oxidation states in certain cases and not the same as we think of in an ionic compound? So, for example, if we take our sodium like we did earlier, plus our chlorine, we're going to get a complete transfer of electrons like we've talked about before, with our metal losing the electrons to our chlorine, going to result in sodium chloride here, basically. And our chloride has our -1 charge that we normally sort of associate with it. This is held together, right, to sodium chloride by an ionic bond. We have a complete transfer of electrons. There's no sharing of electrons. Now, if we take the same chlorine, for example, here, and chlorate, right? Oxidation number of oxygen is -2. That's a -6, a -1. In this particular case, my Cl has what oxidation state? Has a plus. Anyone? It has a +5, perhaps, in this case, right? +5 -6 gives me a -1 in this particular case, right? Now, in this situation, those are two nonmetals, which means if we sketch up our sort of Lewis structure here, 18, 19, 25, 26 valence electrons. So if you sketch up your Lewis structure, looks something like this. They are sharing electrons here, like so, I think. And in this particular case, when we look at chlorine versus oxygen, oxygen is actually more electronegative, which means by sharing these electrons, my electrons are all heading towards the oxygen with the sharing of electrons. If my electrons are going to head closer to the oxygen, that's going to make my chlorine become more and more positive, right? So because it's actually sharing electrons in this case, and the difference in electronegativity of the other elements that it's attached to, where it's sharing electrons, is going to draw the electrons away from the chlorine in this particular case. And in this situation, because of the covalent bonding and the sharing of electrons, it will take on a more positive sort of oxidation state or charge, rather than what we see where it's the recipient of the negatively charged electrons coming in an ionic compound and becomes negatively one charge. Question on that. Gets even worse when you do something like this, right? ClO4 minus, that's a -2, -8, -1, +7 in this case for the chlorine. That's because we now have just added one more oxygen there to suck out the electrons from the chlorine, and thus making it more and more positive, in this case a +7. Not as bad if you take hypochlorite, right? In this case, you know, you got basically just the one oxygen sucking it out, -2, so +1 in this case, and it's not as much of a draw of the electrons away. That is also why when we look at iodine in these two examples, between oxygen and fluorine, fluorine is much more electronegative, right? The most electronegative element you could have. So with that iodine attached to those 7 fluorines, they're all going to suck the electrons way away from the iodine, which is why it ends up at a +7, versus over here where it only has 3 electrons and the iodine ends up at a +5. So not as much of a draw away from them. So this is why when we look at oxidation numbers in states, they're not always the same as what we see in an ionic compound, because in an ionic compound, basically those nonmetals are receiving the electrons, so they're gaining the negative charge and they become those sort of negatively charged things. In certain situations in covalent bonding, those nonmetals are now sharing electrons with things that are more electronegative than themselves, and that's going to draw the electrons away and cause them to have a more positive sort of oxidation state than what we normally associate in an ionic compound. Any questions on that? All right, so now that we have hopefully an understanding of sort of redox reactions and what's happening, let's talk about it in relationship to classifying reactions. So as I mentioned earlier, the redox sort of category is the big umbrella for which we can now classify these type of reactions more specifically. The first type of specific classification is one that is known as a combination or synthesis reaction. And in a combination or synthesis reaction, it is two things make one thing, basically. So in a combination or synthesis, you're basically putting two things together to make one thing. And that is more specifically called a combination or synthesis reaction, but is also in most cases still a redox reaction. That's ultimately what's happening. So if we take aluminum plus some bromine, make a little aluminum bromide, that is, again, two things make one thing. So that is your classic synthesis or combination reaction. It is also still a redox reaction happening. If we look at the aluminum, 0 in terms of the oxidation number. The bromine here is also 0 because that is naturally how it comes. When the aluminum and bromine come together, the aluminum has a +3 charge, the bromine has a -1 charge. So if we just roll our number line here, we could see that our aluminum starts at 0, ends at +3, becoming more positive. So it is the aluminum here going through oxidation. By default, by the way, as soon as I figure that out, I know that this guy is going through reduction, but you could also do it. The bromine starts at 0, ends at -1. So going through reduction here, in that case, becoming more negative. That means that my reducing agent is my aluminum. My oxidizing agent in this case is my bromine. So ultimately what is happening here is the aluminum is giving up its electrons to the bromine, which is what we would expect to happen here, since that is a metal and a non-metal coming together that makes an ionic compound. So in that case, based on all those periodic trends we talked about, the metal should lose electrons to the non-metal, and that's exactly what we're seeing here. Basically, the aluminum is popping the electrons over there to the bromine in this particular case. So you can classify this as a combination or synthesis reaction, which is probably what most people would classify this as, but it is also still a redox reaction that is happening in this case. Any questions on that there? Now, the next type of classification is pretty much the opposite of a synthesis or combination. It's a decomposition reaction. In a decomposition reaction, you're pretty much breaking something apart. So you go from like one thing to a couple of things. It's really the opposite of synthesis or combination, where you put it together. Decomposition, you break it apart. So here we have potassium chlorate breaking apart into potassium chloride and oxygen. So one thing makes two or more things is a decomposition reaction. It is also still a redox reaction that's happening here. Oxygen here on potassium chlorate -2. That's a -6. Potassium is a +1. That means in this particular case, our Cl has a +5 charge or oxidation state. On the right-hand side, potassium has a +1, chloride is -1, and this is 0 in this particular case. So if we look at this, what is happening in terms of oxidation reduction, we look at the potassium on the left is +1, and we look at the potassium on the right, it is +1. Potassium, there's nothing happening, it's just a spectator ion, basically, in this case. If we look at the chlorine on the left-hand side is +5, which would be like here. And on the right-hand side is +1, which would be moving in that direction. It's becoming more negative. So it's actually the chlorine here that is being reduced. The oxygen on the left-hand side is -2, which would be like here. And on the right-hand side, it is 0, which means it is moving in the right-hand way there, becoming more positive. It is actually the oxygen here that is being oxidized in this particular case. That means the chlorine on the left there would be my oxidizing agent, and the oxygen on my left would be my reducing agent in this particular case. So as you can clearly see there, this is also still a redox reaction that's happening. But again, probably most people would classify it a little bit more specifically as a decomposition reaction. And as you can see, clearly there are multiple ways you could classify the same reaction depending on sort of what you're looking at. Any questions on that there? Another type of redox reaction is a combustion reaction. And we'll talk about two types of combustion reactions. One we talked about previously as well, but most people, I would say, if you are talking about a combustion reaction, usually involves some type of organic compound as carbon, hydrogen, or oxygen plus O2 will always make CO2 and water. So that's like your organic combustion, and that's pretty much, in most cases, what people are talking about in terms of a combustion reaction. So like CH4 plus O2, CO2, and water. Basically what happens when you light a Bunsen burner, right? The methane comes out, you light it on fire and makes a reaction. Your basic definition, though, of a combustion reaction is, frankly, all you need to be present is right there. You just need some oxygen, basically. to technically be present for it to be a combustion reaction on the left-hand side of the arrow. And that's what we see here. So this is a combustion reaction. Both of these can be considered a combustion reaction. They are also still a redox or oxidation reduction. Sulfur on the left here is 0. Oxygen on the left is 0 in terms of the oxidation number. On the right-hand side, oxygen is -2. That gives me a -4. That means the sulfur here, to balance it out, has an oxidation state of +4. And if we look at what's happening here, sulfur is starting at 0 and ending at +4. It's becoming more positive. So the sulfur here is being oxidized. Oxygen on the left-hand side is 0 and ends up at -2, becoming more negative, and is being reduced in this case, again, with the sulfur being our reducing agent and the oxygen being our oxidizing agent in this case. So that is definitely can be classified as a combustion reaction. It also can be still classified as a redox reaction. Here's our magnesium and oxygen, 0, 0 in terms of oxidation states. This is an ionic compound, which means normal charges for oxidation states, +1 and -2 in this case. And again, if we see what's happening here, it is what we should expect. The magnesium is starting at 0 and ending at +2, becoming more positive, so is being oxidized because it is a metal, right? And by default, that means that the oxygen here will be reduced. If we look at the oxygen starting at 0 and ending at -2, it is heading to the left there, becoming more negative and becoming reduced in this case. So this basically, as you can see in these 3 reactions here, or these 2 reactions here, for example, this guy right here that we just did, that is 2 things that make one thing could be classified as a combination or synthesis reaction. It involves oxygen, could be classified as combustion reaction, and it's a redox reaction as well. So this one reaction could be classified 3 different ways depending on sort of what you're looking for. The best way would be the most appropriate choice or way of whatever you're looking at there. But technically speaking, all 3 of those classifications would fit this reaction that's happening here. So definitely you could classify a reaction, as you can see, in many different ways, depending on what you're looking at. Any questions on any of that there? Same could be said really for this reaction as well. So another type of redox reaction is a single replacement reaction, and we've seen single replacement reactions a number of times. And they have this general setup where that's an ionic compound. And for example, if this is a metal, it will come in and kick out the positive guy and make a new ionic compound on the other side. We also saw, as we did in that experiment with the halogens, this could also be a non-metal, which means it would kick out the negative guy in that situation and make a new ionic compound, and this guy would come out with no charge. Remember that in order for this reaction to take place, whatever coming in needs to be more reactive than what it is replacing. Now, redox reactions, this is still redox reactions. It is single replacement reactions. And as you can imagine, we could get even more specific in terms of the type of single replacement reaction that's happening here. In this particular case, the strontium is going to come in and kick out the hydrogen. This also can be called more specifically a hydrogen displacement reaction because we're kicking out the hydrogen in this case. This is a 0. Hydrogen is a +1. Oxygen is a -2. On this side, that's a +2 and a 0 in this case. And if we look at what's happening here, strontium on the left is 0. On the right, it is +2, which means it's becoming more positive, so it is being oxidized. The hydrogen on the left is actually +1. And on the right-hand side, it is 0. It's becoming more negative. It is actually the hydrogen here that is being reduced in this case. Obviously, that means this is a redox reaction as well. It's a hydrogen displacement. It's a single replacement reaction that is happening in this particular case. In this case here, this is a metal displacement. We got our metal coming in and kicking out our metal here, basically. So 0 in terms of the oxidation state here. -1 +4, 0 +2 -1. So if we look at the TI in this case, it's going from +4, which is over here, to 0, becoming more negative and being reduced in this case. By default, once again, that means that this guy is being oxidized. And you can see that with the magnesium starting at 0 and ending at +2 here, becoming more positive. And lastly, we could have a halogen displacement like we did in that experiment. Here, again, it's going to kick out the nonmetal in this case. This is 0, +1, -1, +1, -1, and 0. And in this particular case, it is the chlorine and the bromine that's changing. Chlorine starting at 0, ending at -1, moving in a more negative direction and becoming reduced. And the bromine in this case starting at -1 and ending at 0, becoming oxidized. And in this case, once again, our potassium is not doing anything. It is a spectator ion in this case. So these are single replacement reactions, which do fall under the umbrella of redox reaction. As you can see, like I said, you can really get more specific in terms of those types of classifications. Any questions on any of those there? Now, how do we know if a sort of metal or single replacement reaction is going to actually take place? You can use an activity series. You kind of made one in that experiment with the halogens, kind of putting everybody in order in terms of reactivity and stuff like that. A very simple sort of activity series is one where you typically have hydrogen in the middle-ish, and you got elements above and below. And when you look at it, anybody higher on the list will replace anyone lower on the list. And vice versa, anybody lower on the list will not replace anybody higher on the list, so they're less reactive. So you can do that and use an activity series to do that. There's also very specific things that sometimes water is enough to allow this reaction to occur, but sometimes you do need acids to occur. So for example, if we take calcium and water, we find calcium up here. It just needs cold water basically to produce hydrogen gas. So that reaction will take place. If we try to do it with lead and water, lead is lower on the list there, and it needs something more than just water to allow this reaction to take place. It needs hydrogen ions, a lot more hydrogen ions produced by acid to allow this reaction to take place. So it would not take place, but if you took lead with some acid, the reaction would take place. Now, the halogens, as we saw in that experiment, is its own activity series. So group 7 on the periodic table, if you remember, reactivity increases as you go up, right, with fluorine being the most reactive. And that is why in this particular case, chlorine is higher than bromine. So we would expect this reaction to take place and kick out the bromine. But if we look, iodine is lower than bromine. So we would not expect this reaction to take place in this case because iodine is less reactive than bromine. So this reaction would not take place. They again are still redox reactions that are happening here. But again, you can use group 7, the halogens, as sort of an activity series as well. Any questions on that? Now, another type of redox reaction that sort of occurs is an interesting one, and it is one where it is sometimes referred to as a disproportionation reaction. And in a disproportionation reaction, what happens is the same element in that reaction gets both oxidized and reduced at the same time. So it actually, both things are happening to it. So if we look at this one here, we basically have chlorine and we do have some hypochlorite, but we also have some chlorine that ends up over here as just chloride. And in this case, the chlorine is both being, for example, oxidized and reduced. So let's see what's happening in each of these. The oxidation state of Cl2 is 0, -2, +1. So in this case, in the first guy, our chlorine is going from 0 to +1, becoming more positive. So this is being oxidized. In the case of the second one, 0 to -1, our chlorine is going from 0 to -1, becoming more negative, and it is being reduced in this case. So the same element, it is possible for the same element to actually go through oxidation and reduction in the same reaction, and it's what is referred to as disproportionation reaction. Your two half reactions will essentially be these two things here, basically. These are the two real sort of reactions that are taking place. If we look at, for example, our water and our hydroxide, -2, +1, +1, -2. Nothing's happening with the water part of it, or the hydroxide, the oxidation states of those guys are staying the same. It's actually just the chlorine here that is happening, and the same chlorine is both being oxidized and reduced at the same time, again referred to as a disproportionation reaction. Any questions on that there? So it does sometimes happen. So if you come across an equation that you see that happening, it's basically just two half reactions with the same starting guy on each of them, but one will be reduced and one will be oxidized. Any questions on that there? Now, if we look at these here, again, there's different ways we could classify these reactions. That looks like maybe like a precipitation reaction, as that would form a precipitate. That was ammonia, which is our weak base, and an acid, which is H+. So that's like an acid-base reaction, or really a double displacement reaction. This is what we just saw there, single replacement reaction. Which is also a redox reaction, right? That's obviously a double displacement reaction as well. And this is actually two things that make one thing. So that's a synthesis reaction or combination reaction, also a redox reaction. Any question on any of those classifications? So just to summarize the different types of reactions that we talked about here. Do it on here. What we talked about was basically two big sort of umbrellas of reactions, double displacement. And under the double displacement umbrella, you have a precipitation reaction, which again is a more specific reaction that obviously forms a precipitate. A more specific classification is an acid-base reaction that forms water. On the other side, the big umbrella is a redox reaction, which is our transfer of electrons. And more specifically under there, we have our synthesis, our combination reaction. We have our decomposition reaction. We have our single replacement reaction. And we have our combustion reactions, which are, again, more specific ways of classifying them. Between all these different types of classifications, those are the three reasons why a reaction takes place: transfer of electrons, precipitate formed, or water formed. And just so we're clear, there is no redox happening over here. So no transfer of electrons happening in these type of reactions. If you look at the oxidation states or the charges in the precipitation reaction or an acid-base reaction, double displacement, you will see that the charges remain the same on both sides of the arrow. So there's no transfer of electrons happening on the left-hand side there. It's restricted only to those type of reactions on the right-hand side of the slide here. Any questions on that or ways to classify reactions? All right, we will lay it up there for now.